Okay, good morning students. In previous video we have discussed the 0-1 knapsack using the greedy method. Now let us continue with the Kruskal's algorithm. Basically, the Kruskal's algorithm is used to find the minimum cost spanning tree, and it uses the greedy approach. This algorithm treats the graph as a forest, and every node it has an individual tree. A tree connects to another only and only if it has the least cost among all available options and does not violate the MST properties. MST stands for the minimum spanning tree. Now let us go through the coding part of the Kruskal algorithm, and then we'll solve one example. Okay, here we have the class edge, and inside the constructor we will be initializing the values for the variable source, destination, and the weight. The source and the destinations are the vertices, okay, and the weight is the weight between these two edge, source and the destination. Okay, here we are reading the values needed initially, that is the number of vertices. We are storing the values of the number of vertices in the variable n, and also we are reading the weight associated with an edge. Okay, from the source to the destination, the weight values we are reading inside the adjacency matrix using the for loop. Adjacency matrix is the two-dimensional array. Okay, so we can access this two-dimensional array using the index I and j, I for to iterating through the rows and j for to iterating through the columns. That is, for the initial row what we have considered, we continue till all the number of column values are filled up, then we will move on to the next row value. Okay, and also we are creating the edge array to store the edges in each of the index. Okay, the total number of edges without any loops which we can have is n into n minus 1 divided by 2. So the size of the edge array is n into n minus 1 divided by 2. Okay, so again here we will be storing the values into the edge array. Okay, using the, that is by passing the values to the constructor edge. Okay, that is I and j are the source and the destination, and adjacency of I and j is the weight associated with the edge I and j. Okay, these values we will be initializing, and we are creating that is for each edge is a object, and we will be storing inside the array of edge. K is the indices to iterate, okay, or the k is used as index, okay, to move through the edge array. Okay, so we are copying the each edge inside the edge array, and once the edges are copied into the edge array, we will be sorting the edges. Okay, so now up to this part, let us solve an example, then we will continue with. So here I have an example where I am reading the total number of vertices is 6, and we are reading the adjacency matrix. Okay, where we have 0 to 5 as the value representing the each of the vertices, and the weight associated between the two vertices, okay, or between one edge, okay, is given here in the adjacency matrix. Okay, the infinity value represent there is no edge between the vertices, and 0 means we will not be having any cycle. Okay, so values are filled up inside the adjacency matrix. This represents the weight. Okay, now with the usage of the adjacency matrix, I am creating an edge array here. Okay, adjacency matrix is used to access the weight between the source and the destination vertices. So here edge array is created. Totally I have how many edges? It is n into n minus 1 divided by 2, that is 6 into 6 minus 1 by 2, that is 15 edges. That means I can have totally 15 edges inside the edge array. Okay, so to move through the edge array, I have the indices k. The value of the k will vary from 0 to 14. Okay, and with respect to each of the source and by varying the destination, okay, we are assigning the weight. So initially for I is equal to 0, I is equal to 0 means I am selecting the vertices 0, and for the different destination, okay, that means I am connecting the vertices 0 with the other destination like 1, 2, 3, 4 and 5. Okay, so then for these two vertices, what is the edge associated, that I will find from the adjacency matrix. So that weight also I am assigning here. So edge array now is containing the source, destination and weight values with respect to each of the edges. Okay, so like this we will fill up the edge array starting from the index k is equal to 0 to 14. Okay, so once it is done from this edge array, okay, or from the adjacency matrix, we can have the graph like this as we are seeing here. There is edge between 0 to 1, 0 to 3, then 1 to 2, 1 to 3, 2 to 3, 2 to 4 and 2 to 5, finally 4 to 5, and each edge is associated with the weight values. Okay, so once this edge array is created, we have to sort the edges. Okay, after sorting the edges in the ascending order of the weight, I will be getting these many edges. Okay, that is now after sorting the k value will vary from 0 to 8. Okay, to sort the edges, we have the portion of the code here, that is we will be calling the sort method to arrange the edges. So using this portion of the code, okay, we will be arranging, that is depending on the weight value associated with the edges, we will be comparing the weight of the first edge with the next edge. Okay, so which one is the smaller, that will be moved up, and which edge is having the highest weight will be moved down. Okay, so like that we will keep on arranging the edges. Okay, and also after sorting the edge, we are creating the parent array. Using the sort method, we will be sorting the edges. Then using the union and the find method, okay, now we will be finding the minimum cost associated with the minimum spanning tree, okay, as well as the parent for each of the vertices we will be finding. Okay, so after the sort is finished, we have the parent array here, where I am initializing the parent array with the size which is equal to the number of vertices, because the parent array stores the parent of that particular vertices. Okay, the index of the parents represent the vertices, and the value present for that particular vertices is the parent of that particular vertex. Okay, so here we are creating the parent array, and we are initializing all the values inside the parent array with the -1 by invoking the fill method of the class arrays. Okay, so now I will access the each edge which is present in the edge array, and we know that for each of the edge we have the values source, destination and the weight. So now for each of the edge, which one we have accessed through the edge array, I will find the parent of the source and also parent of the destination. Okay, the parent of the source we are representing it as L source, and the parent of the destination we are representing it as L destination. L stands for the leader of the source vertex or leader of the destination vertex. Okay, so once the parent of the source and the destination is found using the find method, okay, that is the find method will search the parent of that particular source or the destination inside the parent array. Okay, so the find method will return the parent of that particular vertex. Okay, so now if once the parent of the source and the destination is found, if both the parents of the source and destination is not same, okay, then only we are going to find out the minimum cost. We are going to update the minimum cost, and also we will be updating the parent of the source in the parent array. Okay, else we will not be doing these two modification. Fine. Okay, so now let us see here with an example. See, here we have the sorted array. Now I am accessing each of the edge from the sorted edge array. Now initially I have got the edge 2 and 4 and its weight is 2. Now I will find the parent of the 2 and also the parent of the 4. The parent of the 2 is 2, parent of the 4 is 4. I will be getting from the parent array by searching. Okay. So that is here the parent of the 2, inside the parent array I have -1, so it will return 2 only. That means initially for all the vertices, okay, the root or the leader parent of that particular vertices will be itself only, because we will be initializing all the values with the -1. Okay, then later on it will the parent array will get modified with the other values. Fine. So initially I will get the parent of the 2 is 2 and parent of the 4 is 4. Now I will compare these two parent values, that is 2 is not equal to 4. Therefore now I am going to find the minimum cost. That is minimum cost is initialized with the value 0. It will get added with the current weight associated with this particular edge what we have selected, that is 2. So minimum cost will be 2 now. And also I will update the parent array. That means for the index 2 of the parent array, I am updating the value with the 4. That is, we have the union method. By invoking the union method, I am updating the parent array after finding the minimum cost. So how the values are updated here inside the parent array? We have the code, the parent of L source is equal to L destination. Therefore, the parent of the vertex 2 is 4 now. Okay. So like this, I will access each of the edge, and depending on whether the parents of that particular edge, source and destination, if it is not equal, then only we will be finding the minimum cost and update the parent array. That means in the parent array, I will be updating the parent of the source vertex as the parent of the destination. Okay. So like this, we will proceed for each of the edge. So as we are proceeding, we are seeing here, initially I have the, in the minimum spanning tree, initially I have got 2 to 4. Then in the second step, 2 to 4, then 4 to 5. Then in the third step, 2 to 4 and 4 to 5, there is an edge. And again each edge is associated with the weight. Then in the for I is equal to 3, we have this minimum spanning tree. Okay. So like this, by applying the same techniques, I will proceed. Okay. So here, as we proceed here, for some of the edges, we will not calculate the minimum cost, and also we will not update the parent. Because why? Because for that particular edge, the parent of the source will be equal to the parent of the destination. Okay. So for those edges, we will not be updating the minimum cost of the spanning tree, as well as we will not be updating the parent array. Because the meaning of this is what? Whenever we have the parent of the source equal to parent of the destination with respect to that particular edge, it leads to the cycle. That means in the minimum spanning tree, when you add that particular edge, we will get the cycle. So we should not have the cycle in the minimum spanning tree. So we will not be adding that particular edge. Okay. So for this type of the edge, we will not be updating the minimum cost and also the parent array. Okay. So here we have an example here. When you consider the edge 3 to 2 and its minimum weight is 4, when you find the parent of the vertex 3, I will get 5 as the parent. Similarly, when you find the parent of the 2, okay, by searching through the parent array, again I am getting parent of the 2 is also equal to 5. Okay. And one more thing here is, in the find method, if the value of that particular vertex is not equal to -1, Okay, the searching will progress by calling the parent method recursively. Okay, so only here, for example, when we are trying to find the parent of the 2, in the parent of the 2 I have the value 4, which is not equal to minus 1. So again I will call the parent of the 4. Again parent of the 4 is 5. Okay, so I will call the parent of the 5 again. So when you are accessing the index 5 inside the parent array, I have the value minus 1. So the procedure stops here. So for the parent of the vertices, for the vertices 2, I will be getting the parent as 5. And for this edge, the parent of the 3 and parent of the 2 both are same. So I will not be adding this edge into the minimum spanning tree because it leads to the cycle. Okay, you can also see if you by drawing that particular edge. Okay, so for the edge 3 to 2, then similarly for the edge 2 to 5, and for the edge 1 to 2. Okay, for all these edges we are not updating the minimum weight as well as we are not updating the parent because we are not considering that edge since it leads to the cycle. Okay, so finally when we consider the edge 0 to 1, here the parent of the 0 is not equal to parent of the 1. Okay, that is parent of the 0 is 0, parent of the vertices 1 is 5. So I will update the minimum cost now and also the parent array. Okay, so finally again if you consider the edge 0 to 3, that edge will not be considering since it leads to a cycle. So finally we will be having this diagram as the minimum spanning tree. Okay, this is the Kruskal algorithm with the usage of the find and the union method. Okay, so that is this to perform these operations we have the portion of the code here. That is here inside the for loop we are accessing the each of the edge. For each of the edge we are finding the source parent and the destination parent using this code find of parent comma edge I of the source. Similarly with respect to the destination, then we have the if loop here to compare the parents of the source and the destination. If both are not same, then using this code minimum cost is equal to minimum cost plus edges I of the weight. We are updating the minimum cost and we are calling the union method to update the parent of the source vertices. Okay, so using this we will find the spanning tree. Okay, so this is the code with respect to the Kruskal algorithm with the usage of union and the find method. Okay, thank you students.